can a computer recognize your face even when the lighting changes completely? If a computer simply compares raw pixel brightness, here's the problem. The exact same patch of skin gives you completely different numbers depending on the light. To a naive algorithm, these could look like two totally different faces. But here's the key insight. Even though the brightness itself completely changes, the relationship between a pixel and its neighbors, which ones are brighter, which ones are darker, tends to stay exactly the same. What if, instead of trusting brightness, we built our entire description around these relationships? This idea, comparing a pixel to its neighbors instead of trusting raw brightness, is exactly what's behind one of the most influential ideas in computer vision: local binary patterns, or for short, LBP. So let's zoom into that little grid and see, step by step, exactly how this comparison trick turns into something a computer can actually compute. All right, let's actually build one of these from scratch, using real numbers. Take the center pixel as your threshold. Now look at each of its 8 neighbors, one at a time. Is it brighter than or equal to the center, or darker? Brighter or equal lights up as a 1. Darker fades to a 0, and this is exactly the example from the original textbook. Same numbers, same logic. Now read those 8 ones and zeros clockwise as a binary number, or just add up the powers of 2 wherever there's a 1. Here, that gives us 53. That single number, between 0 and 255, becomes the label for this 1 pixel's local texture. Naturally, you might ask, why stick to exactly these 8 neighbors? What if we wanted to sample a wider circle or use more sample points for finer detail? This generalizes nicely. Instead of a fixed 3 by 3 square, define a neighborhood by p sample points evenly spaced on a circle of radius r. When a sample point doesn't land exactly on a pixel, we estimate its value using bilinear interpolation, blending the 4 nearest real pixels. Same comparison idea, now flexible in scale and resolution. Here's a neat empirical observation. In real textures, most of these binary rings have at most 2 transitions as you go around. They're called uniform patterns. Patterns with more transitions than that are rare, usually just noise, and they all get lumped into a single catch-all label. Each uniform pattern actually corresponds to a recognizable little microstructure: a spot, a flat area, the end of a line, an edge, or a corner. These 5 categories alone cover a huge share of what's really happening in a textured image. Out of 256 possible patterns, only 58 are uniform, plus 1 shared label for everything else, giving 59 labels in total. And in real images, that's not a minor shortcut. Roughly 90% of all patterns found in real textures, and even in real face images, turn out to be uniform. We're compressing the description without losing the story, so that's the rule for a single pixel. Next, let's zoom back out and see what happens when we apply this to every single pixel on an entire face. Let's apply that same rule to every pixel on a real face. The result: every tiny patch of skin, every wrinkle, every edge around the eyes and mouth now has its own little numeric fingerprint. But there's a catch. If we just count up all the codes across the whole face into one single histogram, we lose all sense of where anything is. Scramble the face into a meaningless puzzle, and mathematically, the histogram doesn't even notice. The fix is simple: divide the face into local regions first, compute a separate histogram for each region, and only then concatenate them all together. Now the description carries both what texture is present and where it is. And that's precisely the structure used in practice: local blocks, local histograms, concatenated into one global facial signature. To recognize a face, we just compare 2 of these histograms, a new photo against a gallery of known faces, bin by bin, region by region, and add up the differences into a single distance score. Here's a refinement: not every facial region is equally informative. Psychophysical studies show the eyes matter more for recognition than, say, the cheeks. So we simply weight each region's contribution to the distance. More important regions count more. And the results back this up. Across several standard face recognition test sets, LBP consistently performs as well as or better than other texture descriptors. Look specifically at the FC column, same person but captured under very different lighting. This is exactly the scenario we opened this video with, and LBP clearly handles it best. This robustness has been pushed even further in practice. Specialized pre-processing for extreme lighting, near-infrared imaging for recognition in near darkness, and probabilistic matching frameworks for even more reliable verification. We've solved the still photo. But what happens when the face is moving in a video?
We've built a descriptor for still photos. But faces aren't static, they move, shift expressions, and change over time. The moment we introduce time, a completely new set of information opens up, containing crucial dynamic details that a static LBP map simply cannot capture. A naive approach would be to apply LBP to every frame independently and compare the histograms. But here's the catch. A subtle microexpression or slow muscle twitch might barely change the global histogram. The critical information is buried in how pixels move over time, not just how they look in a single instant. Here's the key insight. Instead of treating a video as separate images, think of it as a single three-dimensional block, with width and height in space, and time as the third axis. Now every pixel has a trajectory through time. To describe motion, we must capture what happens along that trajectory, not just at a single instant. The first extension is VLBP, or volume LBP. The idea is simple. Add the pixel's value at the previous and next frames as 2 extra comparison points, alongside the 8 spatial neighbors. This gives a 10-bit code, yielding 1024 possible patterns. With multiple histograms, the resulting feature vector becomes enormous, making computation and matching highly expensive. The elegant solution is LBP-TOP, or 3 orthogonal planes. We discard the complex volume code and slice the video block with 3 planes. The spatial XY plane captures static texture, while the XT plane slices horizontally over time to capture left-to-right movement. Similarly, the YT plane slices vertically to capture up and down motion. We run standard LBP on each plane separately, then concatenate their 3 histograms. This 3-plane construction matches the original textbook diagram. 3 planes, 3 histograms, concatenated into a single vector. That is LBP-TOP. Let's look at what each plane captures. XY represents the spatial world textures at a single moment. XT slices time horizontally, capturing sideways movements like the mouth widening. YT slices time vertically, capturing upward movements like a rising eyebrow. Each plane runs standard LBP and builds its own histogram. Finally, just like the spatial regions in Part 3, we concatenate all 3. Just as Part 3 divided the face into spatial blocks to preserve location, here we divide the video volume into local block volumes, small cubes, that are local in both space and time. Each block volume runs LBP-TOP on its 3 planes, contributing its own histograms to the final vector. This creates a descriptor that captures not just what texture occurs, but where and when. Once again, this matches the textbook exactly. The video block volumes are processed by LBP-TOP and concatenated. This long feature vector forms a complete spatiotemporal descriptor, ready to compare against a gallery of expressions or identities. Back in Part 2, we chose neighborhoods by radius r and sample points p. But which scale should you actually use? The answer depends on what you're detecting. Fine surface texture requires a small circle, while larger structures need a wider radius. Often, you need multiple scales at once. The solution is simple. Run LBP at several radii simultaneously. A small radius captures fine local microstructure like skin pores. A medium radius picks up wrinkles and muscle movement patterns. A larger radius describes the broader structural geometry. Each scale produces a histogram, and we concatenate them into one descriptor. It's the same comparison trick, applied at multiple zoom levels. Here is the intuition. Look at the corner of the mouth. A tiny neighborhood sees only skin microstructure. A medium neighborhood captures the lip curve and local muscle lines. A large neighborhood places that point within the broader face geometry. These are all useful signals. Losing any of them costs information. Yet running all 3 costs almost nothing extra. It's the same algorithm at different radii. Remarkably, LBP is not just for face recognition. The same comparison operator shows up in almost every face analysis task, facial expression, gender, age, face detection, iris recognition, and pose estimation. It also combines powerfully with other tools like pairing, LBP with active shape models to anchor texture description at detected facial landmarks. For expressions, LBP faces a location problem. The face is covered in thousands of overlapping windows across multiple scales, but not all distinguish a smile from a frown. This is where AdaBoost helps. It sweeps the candidate features and selects only the most discriminative ones for each expression pair. This yields a compact, targeted feature vector, eliminating wasted computation. Where does LBP sit among face descriptors? Basic LBP is simple and fast, occupying the low-cost zone. But adding spatial blocks, regional weighting, and multiple scales boosts its descriptive power significantly. It remains far cheaper than heavy alternatives like Gabor filters or SIFT. This high-efficiency trade-off made LBP a foundational baseline that almost every subsequent method is compared against. Granted, deep convolutional neural networks now eclipse LBP in accuracy on massive benchmarks. If you have millions of labeled images and a GPU cluster, use a CNN. But in resource-limited scenarios, embedded medical cameras, mobile systems, or domains with tiny datasets, LBP remains the default. It is fast, interpretable, and requires minimal data. These ideas are very much alive in production systems today. Let's close the loop. We started with a problem, raw brightness lies. We solved it by comparing relationships rather than absolute values, encoding them into local binary codes. We made these codes flexible with PR neighborhoods, organized them into spatial histograms, weighted regions by importance, extended to time with orthogonal planes, divided videos into block volumes, and ran them at multiple scales. That is the complete LBP story, from a single 3x3 grid to a Spatiotemporal descriptor. And that is LBP, a 3x3 window, a simple comparison, and a clever observation. What matters is not brightness itself, but the pattern of relative brightness. It is fast enough for real-time, robust against lighting changes, and flexible enough to extend to video and multiple scales. It remains a trusted baseline of facial analysis research for 2 decades. If you found this useful, please like and subscribe. See you in the next one.